Let's go for your isobaric. Isobaric. What is going to be happening here?
Irreversible. I mean, delta P is 0.
Delta P is 0. So what does that mean? In this
It's an
particular case,
irreversible
P
process.
external is P internal,
Yes.
meaning we end up having in this particular case here work done.
Initial. That is. Yeah.
Whether it is irreversible or reversible, works out as what?
P, P delta V. Yeah.
P delta V. Minus P delta V.
Ah, yes.
Okay. Yeah. Now, in this case here, what will Q be? Q is at isobaric, na, constant pressure, right? So I'm going to represent it as QP.
Okay. Yeah.
How will I write this Q here? How will I find this Q here? That has to be found using delta U, correct?
Delta U.
Delta U is going to be Q plus work done. So in this case, मुझे work done पता है, easily मिल जाएगा, because this is easier to find here, correct?
Yes. Yeah.
Yes or no?
Yes.
It's easier to find here. So I can now calculate this work done a little bit more easily because it is minus P into delta V. The delta U is actually the more complicated one to calculate here, not QP. The QP here generally for this kind of a thing can be calculated quite easily as simply NCP into delta T. But people did not know this in the beginning. Can we clearly do?
Yes, sir.
So people did not know this properly in the beginning yet. This did not make clear-cut sense at that time. NCP, they did not know what CP meant at that time. They knew this, but they did not exactly know. So when you're going to be looking at this QP here, this is going to be something which will be delta U minus work done. So you can think of it as delta U plus P delta V. This is going to be your QP over here. Now, of course, this is effectively what changes into your delta H.
Oh,
Why? Because at constant pressure, what is H defined as? U plus
U
P.
plus PV. Yes.
So if I write delta H, I can write it as delta U plus delta of PV.
So we can say Q at
Yes.
constant pressure is nothing but
So
delta H.
this lead to delta H works out as delta U plus P delta V plus V delta P.
But V delta P is 0.
Correct. So at delta P equals 0 implies delta H simply becomes delta U plus P delta V, which is of course going to be your heat change at constant pressure. You understand the principle over here?
Yes, sir.
What did I tell you about heat change at constant pressure?
So,
This flow is a state function.
oh, that's, oh, yes. Yeah.
You remember the point here?
Yes, sir. Yeah. Yes.
So the reason why I'm trying to connect the pieces now is, see, I
Oh,
gave you the story earlier. Now I'm going to connect the pieces.
mathematically.
So you're going to be having delta H actually being a state function, mainly because it is related to the QP. Then. It is
Okay.
it is literally nothing but QP. It cannot be anything else but QP. Now,
Yeah.
next, let's go for isochoric.
Yeah.
So if it is an isochoric process, what does that mean?
Delta V 0.
Perfect. So delta V is 0 now. We'll have what being 0 here?
Directly. Work done is 0.
Work done is 0. That means directly I will have delta U here.
Delta Q. Yes. QV. Yes.
Again, straightforward state function. Right? And you can write this state function as what? N into CV into delta T.
Yeah.
And what is my delta H being written as?
Delta H. Delta U plus delta
That is
PV.
true. What can I write it as? In this fashion. N into
Oh,
CV
NCP delta
into
T. Oh,
delta T.
sorry. Yes. Yeah. NCP delta T.
Correct. Now what do you see? You can see that internal energy is a function of what? Number of moles temperature and CV.
Volume.
Not volume, CV.
Sorry. V is constant volume. Yeah.
Let's not consider it as CV really. We'll think about what CV is in a little bit of time. And lastly, what is H going to be?
Function of N, T, and then CP.
CP. So what is CV really going to be? What is this guy truly? Heat capacity for a particular mixture or a substance at constant volume, correct? What does that really mean? What does it depend on? We are trying to see dependencies now. I'm going to connect it back to the same shit I gave you in the beginning.
Also depends on temperature.
I gave you some crap in the beginning today, na? This crap. We are going to connect it back over here. Are you able to see my screen there a bit more clear?
Yes. Yeah.
Okay. So we are going to be connecting it back to this bit over here. How do we link it back? We have got the P part here, N part here. Now, the CV and the CP, they will change if I'm going to be having a phase change or a reaction happening.
Oh, I see.
You understand the idea here? So the CV or CP changes
State.
if phase change or reaction. So both of these will remain the same if there is no phase change or reaction. So my U and H are going to be remaining the same if there is no phase change or reaction, no temperature change, and finally what else? No number of moles change.
Okay.
Clear so far?
Yes.
So now lastly, let me give you the last puzzle. Now we are not going to be solving this puzzle today. We are going to be solving this a little later. Now, when you're going to be having an adiabatic process, what is kept zero here?
Heat.
Heat is kept zero. So if I'm keeping heat as zero here, what happens here? I have delta U working out as work done adiabatic. Plus, of course, heat, but the heat is zero. Right, so this bugger is zero. That means I will straight away have delta U for adiabatic.
Minus, say, plus.
For adiabatic is going to be work done adiabatic. Correct?
Yeah.
Now, is work done easy to calculate or tough to calculate? Experimentally speaking.
Oh, work done is
Much tougher to calculate.
tougher. Yes.
Especially in something like an adiabatic, it is going to be a lot more complicated to calculate.
Yeah, it's fast. So
Now, if I'm going to be having something like this, how would I sit and get anything out here? Everything seems complicated here now. What is easiest to calculate normally for us?
Heat.
What does heat mean? What are we? Why is heat easy to calculate?
Temperature difference.
You got to the correct point now. So let us now observe this adiabatic a little bit more closely. So state S1 linear is going to state S2. Okay. State S1 is going to be P1, V1, T1. State S2, I'm going to take it as P2, V2, T2. Okay. Number of moles, I keep a constant. Now, I want to find out work done adiabatic. Let's assume it's reversible. Reversible also works, but reversible or irreversible, let's actually first not make the question up. We'll keep it open. So, what is going to be the easiest way to calculate my work done here? Now, let me tell you what happens over here. Work done here is far more complicated to calculate. But delta U is a state function.
Hmm.
This guy is a state function.
Yes.
So this fellow you can calculate in this fashion,
NCV.
right? And then link it up to this book.
Oh. So
That will also work as a way to check if all of the shit which you have done is correct or not.
sir, but then why would delta U adiabatic be equal to delta U and its constant value?
Think, what is delta U?
Change in return.
So if I'm going to be having, say, state S1 being, say, P1, V1, T1, and number of moles N. Okay. If I have a theoretical state S3, okay, where I'm going to be having the pressure being P3, my volume is maintained as V1, and my temperature is finally become T2. Number of moles maintains the same.
Yeah.
Now, if I'm looking at delta U, let's call this as process 1. Process 1 is the guy in red. Process 2 is the guy in blue. Okay. Now, what is delta U for process 1?
Delta U.
Delta U for process 1 can be effectively written as work done divided. Correct?
Yes.
Delta U for process 1, it is internal energy, correct?
Yeah.
So it depends on temperature and number of moles.
Yes.
It doesn't matter what is the pressure, volume, and shit like that, correct?
Yeah, correct.
So I can say this delta U is going to be a function of the temperature and number of moles. Meaning it is going to be a function of the delta T involved here and the number of moles.
The second process is the same. Okay.
Now let's look at the second process here. In this second process here, I am going to be having the same delta U. Delta U in P2 is actually going to be the same as the delta U in P1. Excepting in this second process here, the delta U is going to be, instead of work done adiabatic here, this is not going to be something else. This is going to be an isochoric process.
Yeah.
So it will be heat change at constant volume.
Yeah.
You understand the idea here?
Okay.
Do you understand how we connect things over here?
Yes, sir. Got it. Yeah.
So the idea here is this is a completely theoretical step.
Yeah.
This is not really done at all.
Yeah, just to prove it. Yeah.
But the mathematics should work if delta U is properly a state function.
Yeah, we proved it is. Okay.
You understand the idea here, right?
Yes. Yeah.
So if delta U is working like a state function, this should be working.
Yeah.
All of this is based on that shit only, correct?
Yes.
So if delta U is a clear-cut state function, my delta U in process 1 should be equal to delta U in process 2, which means my work done adiabatic there should be my QV in this second process.
Okay. Yeah.
समझ में आ रहा है कि क्या हो रहा है?
Yes, sir.
So now from there we'll be calculating the work done adiabatic. Now if I want to calculate the work done adiabatic, I will still be getting QV here, correct? So QV now I'll have to write it as NCV into T2 minus T1. Correct?
Yeah.
CV is what? For a gas, we will effectively be getting Cp by Cv being a new term called gamma. I'm assuming this is familiar for you?
Yes. Yeah.
Now, so if Cp by Cv is this, another relationship between Cp and Cv is Cp minus Cv.
Yeah.
We'll derive this thing in the next session when we are discussing delta H and delta U link.
Yeah.
But I'm assuming this is familiar to you. So substituting
Yes.
that, you'll be getting CV will work out as R by gamma minus 1.
Hmm.
So you'll end up having this as N into R by gamma minus 1 into T2 minus T1. This is going to be your
What?
QV, or you can also call it as work done adiabatic.
Hmm. Exactly. Yeah.
You understood the process here so far?
Yes, sir. Yeah.
We will talk a little bit more about this because this is not over. The game has only started. Because in questions where you have to calculate work done adiabatic, people are not going to be stupid and give you data directly. Adiabatic type, there are two types of things. In this case, you need temperature, T2 and T1. They will generally not give you this.
You have to find it through another thing.
Yes, ये मिलेगा नहीं तुम्हें. If it is a reversible process, you can apply your adiabatic rules. PV power gamma equal to a constant and calculate your T2. You understand what I mean by that?
Hmm. Okay.
We'll talk about that in the next session. Because
Hmm.
much more complicated thing. We'll close here today. You have enough on your plate now. So in the next session, we'll continue on our work done journey and we will move into how to finish up the calculations for work done adiabatic.
Hmm. Okay.
Good luck for your exam tomorrow, dude.
Yes,
Do
sir.
not
Yeah.
screw it up.
Yeah.
I do not want blood on my hands unnecessarily.
Yes, sir.
Uh, so to say, good luck. Do well.
Yes. Thank you,
Bye.
sir. Yeah.
Any questions?
No, sir. I am not.
Okay, all right. I've
Sir,
confused
can
you.
you share the thing?